Hello everyone, this is Rashida. My today's topic will be loss or cost function. In my last video, I explained in details how a neural network works. And in my video, I already mentioned cost function, but cost function is actually a very core concept when it comes to machine learning optimization. And before we dive into neural network, we should know about cost function in details. Loss and cost functions are the similar ideas, but loss is the difference between the label of one training example and corresponding predicted label. The average loss of an entire training dataset refers to as cost function. Let's look at an example. Say this is the dataset. Let's say in this dataset, this volume is the label or the target variable. And we will take one of the training example, like let's say the first row of the data only. Let's assume our model predicted our first row 18900,567. So this is the output coming from the model. Now, what is the difference? This one, this is minus this. So this is the difference. Now, if we take the predicted output or predicted label for all of it, all of the data, and the difference of all of the data, and then the average of all the differences, that becomes the cost function. As we just saw, cost function tells us how well the model prediction matches with the true label, or it measures the performance of the model. If the cost function provides a higher value, that means the prediction is far away from the true label and we need to optimize the model weights a lot more. In my machine learning series, I used mostly scikit-learn library to develop the machine learning models. So we didn't actually see what's going on behind the scene. But all the machine learning models like linear regression, polynomial regression, support vector machine, logistic regression use cost function for the training phase. As we saw in the last video, neural networks uses cost function for the model optimization as well. Cost functions are different for regression classification. In this video, we'll focus on the different cost functions in regression. Regression models are used to predict the continuous variables like age, salary, price, or loan amount. The cost function for these kind of models are usually distance-based. For example, let's say the actual label is y and the predicted label is y prime. The error becomes y minus y prime. Simple, right? And most commonly used cost functions for regression models are based on this error term. One very popular cost function for regression models is mean squared error. So as usual, the error y minus y prime, but what it does, it just takes the squared of all the error terms of all the training examples and divide it by n, the number of training data. So that is the mean square error. And mean square error penalizes high errors caused by outliers. Because you can see when you take the square of the error, it becomes really large. So when there is a value that is an outlier, which is much higher than everything else, then that much higher value becomes even much, much larger, right? So it's very sensitive to outliers. The next one is root mean squared error. It's pretty much like this one, mean squared error, but it just takes the square root of the mean square error. This one also penalizes high errors caused by outliers, but not as much as mean squared error, because as you can see, we take a square root. It minimizes the penalty a little bit, but still it's sensitive to outliers. The next one is mean absolute error. So you can see again we use the error here, y minus y prime, the difference between actual label and the predicted label. And then we take the absolute values of the error. So negative values do not cancel out the positives. You take sum of all the errors of the training examples and divide it by the number of training data. Mean absolute error, or MAE, is more robust to outliers because it does not penalize high errors caused by outliers. But it has a drawback. It is not differentiable when the error is zero. If you remember calculus, you understand what I'm saying. Otherwise, don't worry about it. Many machine learning models, including neural networks, involved differentiation for optimization. MAE or mean absolute error is not suitable in those cases, but it is still good for model evaluation. The last one I'm going to talk about today is root mean squared logarithmic error. You can see it has almost the same thing as a root mean squared error, like taking the differences and squared and then square root. But it just includes a log behind. So it's log y plus 1. This yi is the true label minus log yi prime plus 1. So yi prime is the predicted label. We add 1 to both true label and predicted label just to avoid any zeros. And then you take square of these differences. And finally, the square root. So that becomes root mean squared logarithmic error. So this is robust to outliers. It doesn't penalize for outliers. And large errors and small errors are all treated equal. That's all I wanted to share with you today. In my next video, I will talk about the cost functions of classification model, which will be much different than these ones. So stay tuned and like, comment, share, and subscribe. Thank you so much for watching.